Hi, this is Andrew. Thanks for joining me. Today's video is about subnetting, specifically with IPv4. So because it's such a long video, I'm going to break it up into sections. You can go into the description, pick out the sections that you're interested in, or just watch the whole thing straight through. We're going to start out by talking about subnetting a little bit, drawing a picture that kind of helps to explain it, and then get into the calculations of it, how to use the magic number, why the magic number works, and then we're going to get into 3 examples for subnetting that you can pause the video, I'll put the example on the screen, and then come back to the video and make sure that you did it correctly. So then we'll do variable length subnet mask. Slightly more confusing, but really follows the same process. Give you some examples there as well. So with that, let's get started. Okay, we're going to start by just drawing out what we have here. So I'm going to just go with 192.168.1.0. That's our /24. So what this is an IP address and the 24 says that the 3 octets to the left of this line are all the network address, and then the 1 octet to the right of this line is the host. And that's because we're saying that subnet mask is 24 bits long, and that means 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. There's our subnet mask written out in binary. Now, if we want to do, I could write zeros here and all the way across 8 zeros. So what we have here is a single IP address that has 254 usable addresses. There are actually 256 numbers. And if I were to draw the number line out, we would have a number line here that goes from 0 to 255. Now, that's because that's what 8 bits can represent. If we just do the calculations or based on history, there are 8 bits you can represent 255 possible numbers. So in this case, all we're looking at is this last octet here. And I'll do that in blue here. This is the only octet that matters. Everything to the left in this case is just going to always be the same. If we subnet 192.168.1, we'll start everything we're doing. So right now we have 0 to 255, and 0 is the network address, so we can't use that number. 255 is the broadcast address. We can't use that number. So that leaves us with 254 usable addresses. Now, let's say we did want to subnet this. For some reason, we don't want a single network with 254 addresses. We want to break it into 2 separate networks. So what we can do there is we can say, I'm going to draw a line here. And it's going to be broken in half, and we're going to have this number goes to 127, and it starts at 128. So now we have 2 networks. And in order to do this, we need to take one of the bits that's being used in this host and turn it into a network address also. So instead of starting out with the 0, we now have, in this scenario, a 1. And then 0 all the way out. 7 zeros in this case. Now, as a result, 0 and 127 can't be used. That's the network address. That is the broadcast address for this network. And then 128 through 255, 128 and 255 can't be used. And if we wanted to, we could keep going there. So that's the whole purpose of behind subnetting. Maybe we have a 4-story building and we want a separate subnet for each floor. Or we have 4 departments and we want to break it up by departments. This is sales, this is IT, and so on. We have different departments. We want different subnets to isolate their network traffic. So this is what we're doing. Now, if you look at it and you say, okay, half of 255, that's 127, 128. So we could just take the numbers and we could say half of 128 is 64. So we go to 63. This just gets a little bit harder to do the math, and it's very easy to make mistakes. So the next thing of importance is figuring out how many addresses we have in here. So in this case, I actually took this one step further. We went from having one subnet bit in the last octet to 2. So that leaves us with 6 zeros. So what we can do is we can do a calculation to say how many IP or how many networks do we have. Let's start there. If we look at this, we can count out 4. The way we get to that 4 is we say 2 to the n, and that number, that n, is how many bits we have right here. So before we had 1, and that left us with 2 networks. 2 to the first power is 1. Now we can do it this way also. 2 to the second power is 4. So with 2 networks, that's 4. That is how many networks we have here. If for some reason we wanted to break it down again, we have 3 networks. 2 to the third power is 8. Use your fingers if you're stuck on this. 2 times 2 is 4 times 2 is 8. That's 2 to the third power. So that's all we're doing here, is we're just calculating out how many networks. Now the calculation on, let's clear that out of the way. The calculation for the number of hosts in each network is just a little bit different. It's 2 to the n, which is how many bits. In this case, n is the bits that are in blue, the number of zeros we have, minus 2. And that minus 2 is because the first and last number in each one. And in this case, the last, we have 64 and 63. So 0 to 63 is the first subnet. We have 6 bits that created that. We can't use 0, we can't use 63. So the number of usable bits we have is 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. So we got to the 6th bit. So 2 to the 6th power, let's draw this one in blue. 2 to the 6th power is 64 minus 2 is 62. And if we just look at where those numbers are, we're really counting from, we don't count 0, so we're counting from 1, and we don't count 63, so we're counting to 62. In that case, it's very clear that we have 62 hosts available. In later cases, it's just a little bit harder to do the math. And even here, it's, it can be a little bit harder. So just keep in mind that it's 2 to the 6th power, or 2 to the n power. And n is the number of blue bits we have. So that is how we calculate out. Frequently, we're doing that calculation backwards. We're saying we need 50 IP addresses for sales. So we have to figure out, if we do 2 to the 6th minus 2, we get 62. If we do 2 to the 5th minus 2, we only get 30 IP addresses. So that's not enough. So we'll see that later on in our examples, that the number of hosts that we have is frequently the way you look at it, rather than the number of IP addresses are available. It's just looking at it backwards. So let's get started with actually subnetting the way you would when you're either taking a test or doing this in the real world. So anytime I'm subnetting, I like to start out with having all of the binary numbers, the decimal representations of the binary numbers just written down. When I am taking a Cisco exam, I'll even write down, it used to be on a piece of paper, now it's on a whiteboard if you're taking it in their environment. I haven't taken one remotely yet, but at some point I will. I want to see these numbers, I want to be able to visualize them. It just helps me to put my finger on something and say, this is where we're working from. So what these numbers represent are the values of each bit in an octet. So if you can represent any number between 0 and 255 this way. So let's go back to our previous example, or what we wound up with in our previous example. I'm going to let's look at IP address 60, and because we had the two extra bits, we're going to go with a 26. So what we're saying, if we go back to here, is we have 24 bits for the subnet mask that cover the first three octets, and 2 bits in the last octet. So we're just doing that right here. Now, what does that mean? That means that our subnet mask is 1, 1, and then zeros. So this is the network portion of our IP address, and that means that these 2 bits are the network portion. Now, that means that 64, I'm going to go do the magic number method. 64 is our magic number. That's the number that tells us how we can count to calculate out all of our networks. So I'm going to just start typing them out. 192.168.1.0 is our first network, /26. 192.168.1.64 is our next, because our magic number is 64. So we just count by 64. This is our octet of interest, our 4th octet, and we just count by 64. 192.168.1.128 /26, and then 192.168.1.64 plus 128 is 192.26, and then those are the 4 networks. And because we know 2 to the second power is 4, that's all of the networks. I like to, just to help visualize, and sometimes we're going with larger numbers and we'll skip over sections. If we add 32 to 192, we get 256, which is not part of the network. It's an impossible number in an 8-bit environment, but it helps to visualize what happens next. When we're dealing with subnetting, we're looking for 4 things. We're looking for a network number, we're looking for a broadcast address, we're looking for the first usable IP address and the last usable IP address. Going back to our whiteboard, we have the first octet, or the first network is 0. The broadcast address is 63, and then our first usable is 1 and our last usable is 62. So back here, that's what we write down. We have, this is our network, then we'll do first, last, and broadcast. So our first, I start with broadcast. So our broadcast is 63. Then we can fill in. Our first is 1 more than our network, which is 1. Our last is 1 less than our broadcast, which is 62. And that's it. Now we'll do the same thing with this one. We'll go to our broadcast, which is 1 less than the 128, 1 less than the next network. So it's 127, which means our first usable is 65, 1 more than 64. Our last usable is 126. And we'll just keep going with that. The 192 is the next network, so our broadcast is 191. And our first is 127. Let's put a space there. Our last is 190. And let's do the last one. Now this is why I like to write down this last address here, this fake address, this imaginary address. It's just a reminder that 255 is your broadcast. You could always say, oh, this is the last network, 255 is a broadcast, and yeah, that works. But I like to, it helps to visualize it. If it doesn't help you, that's fine. So 193 and 254, first and last. So we have now subnetted this into 4 subnets. Now if we look back at that 60, we're saying we have 60 as an IP address. And all we have to do is figure out which network it fits into. Is it between 1 and 62? In this case, sure, yes it is. So 60 is in the first network. Now if we had a follow-up, if it was 68, that would be in the second network. Now what kind of questions can we answer with this? Obviously a simple one is just to say these two addresses, are they on the same network? Is 192.168.1.60/26 on the same network as 192.168.1.68/26? The reason that you might need to know that is when your computer is communicating with another computer, when 60 is communicating with 68, knowing that they're on the same network will let you know, is it going to go through the, is it going to communicate directly, or is it going to go through the default gateway? Or it could be that the default gateway is 65 and you look at 60 and you'll say, wait a second, the default gateway can't be on a separate network. So that's an answer to a question. These can be simple short answer multiple choice where there's only one solution. You need to change the default gateway, or you need to change the IP address. Or it can be more complicated where it's a practical example and they say use the first address on the second network for the IT department router. So that's 65. If you have this all drawn out, that makes the next step where they say use this number for this thing a lot easier. And it might be they say use the last for the switch VLAN, or use the second for PCA. So these are all questions that can be answered with this with subnetting. So the final piece of looking at magic numbers is, why does it work? Why do we say that this number 32 is our magic number and our IP addresses increase, our network addresses increase by 192.168.1.0 and then 192.168.1.32 and 192.168.1.64, so on? Well, the answer is because what we're looking at here, when we are subnetting, this is our subnet mask. What we're looking at are all the possible values. In a network address, all of the hosts are 0. We're looking at all of the possible values that can come if we cycle through these numbers. So the first thing we would do is 0, 0, 0, and then all of the host numbers are 0. And that translates to 0. Then the next one, if we increase it by 1, we get 0, 0, 1. 0, 0, 0, 0, 0. And that is 32. And if we count by binary, it's just like counting by decimal. The next thing is 0, 1, 0. Because if we add 1 to what's happening on this side of things, we add 1 to that, we add 1 to 0, 0, 1, we get 0, 1, 0. Now, that is 64. What's next? We go 0, 1, 1, 0, 0, 0, 0, 0. Because we add 1 to 0, 1, 0, and we're adding 1 to this last position. That gets us to 96. And if you look down here, that's the pattern that's going on here. It's just because of the way binary counts. So if we were to continue through all of this, we would see this number 32 flipping back and forth. That's why we can count by 32, because it's really just each time we add 1 to this, we're adding 1 to this last column, which is 32. Everything else stays zeros. Now, the other piece of it is, what is the broadcast address of all of these? Well, if we want to calculate the broadcast address, we turn all of these host bits into ones. 1, 1, 1, 1, 1. And this number is going to be 1 less than 32. Because if we added 1 there, it turns this into a 0, carry the 1, 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 and we have 1 there. But let's actually do it the other way. 16 plus 8 is 24, plus 4 is 28, plus 2 is 30, plus 1 is 31. There's our broadcast address. Same thing happens every step of the way. It's just one less than this one. And if we want to look at the last usable address, we have 0 there, and the first usable address puts a 1 here, and zeros in all of these spots. So these are all shortcuts for doing all of this binary. And they are shortcuts to the point that you can actually frequently just do them in your head. Some of these questions will look so simple to you. All you have to do is figure out the magic number. And 27, the magic number is always going to be 32. You're always going to be counting by 32s. I prefer to see the numbers here, so I'm not relying on my memory. I prefer to actually see them, and that's why I write them out. So let's go through a few examples now. Okay, for example 1, we're going to take the 172.16.0.0/24 network and divide it into 8 subnets. So we'll say 8 subnets here. Now, just because it's 172.16 doesn't make any difference. We're still looking at the 4th octet. That's the octet of interest. So in order to get 8 subnets, the question is, how many networking bits do we need to use? So just remember, 2 to the n. We have 2 times 2 is 4. So 2 bits is not enough. We need that 3rd bit to get to 8. So our subnet mask will be 1, 1, 1. Those are our 3 network bits, followed by 5 zeros. Those are our 5 host bits. And just remembering the math, 2 to the n is the networks. We have 8 of those. 2 to the n minus 2 for the number of hosts. We have 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. That's 5. Minus 2. We have 30. So we have 30 hosts. That was not part of the question, just something to be able to answer. So what do we need to do? We need to figure out what are our subnets, and we can come up with all 4 of the items. So this is our magic number. We will highlight that, and so our first network is 172.16.0.0/27, because we had 24 bits, we added 3 more, 27. And that is network. And we'll come back and get the first, last, and broadcast. So second is 172.16.0.032/27. Third, 172.16.0.64. And we won't go all the way with these because we're just counting by 32s. But then we have 172.16.0.96 and /27. Now we're going to see later on why it's important to have the /27 on each network, because that is what defines that. And 128/27. And I'll do ... We could continue going all the way with this, but we're going to stop there. So now we're looking at our, we'll go for our broadcast, which is 172.16.0, and 1 less than 32 is 31. And we'll do our first, which is obviously 1. Our last is 30. And if you remember, we said 30 hosts, 1 through 30. Now we go to the next one, and we have 172.16.0.63, because that's 1 less than the 64 we have right here. So now we can put 33 as our first, and 62 as our last. Again, the math is very easy. In most cases, it's adding 1, subtracting 1. 172, 16, 0 dot, let's see what our next network is, 96, so we have 95. So we have 65 and 94. And the process just continues on and on. I'm not going to type them all out. So what did we do here? We created 8 subnets that had 30 hosts in each. For example 2, this one is a little more complicated, but if we follow the same process, everything still works. So we're looking at 10.0.0.0/16. So right now it is the left half of this is the network and the right half is being used for hosts. So what we want to do is create a network or create networks that have 500 hosts. And this is kind of different because it puts the octet of interest into the third octet. We can't get 500 hosts out of this last octet. So we need to be in the third octet. Now, just take a step to think about that. That means that we have 8 bits here. That gets us 254 devices. If we add one more bit, that almost doubles it. That gets us to 510 devices. Just 2 to the n minus 2. 256, 512 minus 2 is 510. So we need one more bit here. So what does that mean? We have, we're looking at it from the host perspective. So we need network bits all the way there. We only need one host bit there. Remember, this is the third octet we're looking at. So our magic number is now 2, which is kind of different from what we've seen, but the process is still the same. So our first network is 10.0.0.0, and instead of /16, we have 7 more than that, because we have 16 gets us to here, the first 2 octets, and we have 7 bits in the third octet that are part of the network. So 16 plus 7 is 23, and that is our first network. So let's just label it. Now we're going to come back and start looking at the rest of the process at the first, last, and broadcast. This is where it gets a tiny bit more confusing, but thinking it through, it's not that bad. Now we're counting by 2s, but we're counting in the third octet. 2 and 0 /23 and 10.0.4.0/23. 10.0.6.0/23. Now we can keep going like that for a really long time, obviously. So, but we're going to stop with that. We're going to have network. We have first, we have last, and then we have broadcast. So let's give a little more space for these. And we're not going to look at first, we're going to look at broadcast first. So broadcast is 1 less. 10.0. Now we can say 1, but it's not 1.0 because it is 1 less on the last octet. So if we drop 2.0 by 1, it's basically like carrying numbers. We're saying that is 1.255. That is the last network we can make, because there is no 1.256, and if we add 1 to this, we carry it flips over, and now we increase this by 1. That gets us to 2.0. So that's the hardest part of not working in the last octet, is that one piece. Now if we go back, obviously first and last now become easy. 10.0.0.1. Last is 10.0.1.254. Let's pull that back. So 0.1 is the first, 1.254 is the last, and those are in the same subnet. So we can continue on here. Now it's the same process, 0 dot. Now the next network is 4, so this one is 3.255. That's our broadcast. The last possible address. 10.0.2.1. 10.0.3.254. So there's our second network. We can continue on. Third network will be the same process, and we'll stop there. 10.0.5.255. If you look at it, the pattern is continuing. 135, and it's going to be 135.024. And it's because we have two networks, and if we doubled that, we'd be counting by 4s instead. So if we said we needed 1,000 hosts, we need one more bit for that. So we'll just fill in this one and stop there. This one is 4.1, and then we have 10.0.5.254. So there's our subnetting. Again, we could keep going for a long time with this one. That is example 2. For example 3, we're going to come up with a very specific question. So this is very similar to what we've seen before, 192.168.1.60/27. But it has a question. It's not just list out the networks, but we're going to wind up doing that anyway. What is the highest IP address in the network? And this might be because you have to set that as a switch VLAN address, or it might be that it's just a straight up question, what's the highest IP address in the network, or it's asking you something else related to that. And this is, again, these are things we've done before. And I'll add highest usable address, just so we can clarify it's not the broadcast address we're looking for. So /27. Remember, the 24 bits are the 3 octets on the left. This is the last octet. That leaves us 3 ones here. 1, 1, 1, 0, 0, 0, 0, 0. What is the so before we get there, let's look at our magic number is 32. 192.168.1.0/27, and then 192.168.1.32/27, 192.168.1.64/27. And now we're looking at the IP address 60. Clearly that falls in between the second and third network we have listed here. So really it's the second network we care about. So broadcast is going to be 192.168.1.63, which is one less than the 1.64. And then we have our IP addresses, which are 192.168. 1.33, and we'll just do a dash to say through 62. That's our IP address range. So the highest IP address is going to be 192.168.1.62. There we go. That answered the question. So far, we've looked at situations where the subnet mask is the same throughout the entire larger network. We use the same subnet size for everything. So if we're drawing a picture of it with our number line going from 0 to 255, since they're all the same, that would be a /26 subnet mask. If we wanted a /27, now we just divide again. And remember, from /27, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 subnets. Now, what if you had a situation where one department had more people than another, or different needs? And we start by breaking it in half. But that's not quite good enough. So we need we need 126 or 100 or something like that in subnet A. But then subnet B can be smaller or needs to be smaller. Well, in that case, we can do this, B. And we could even do this and have C. These are subnets A, B, C, and D. And just looking at it from a number line perspective, A goes up to 127, B starts at 128, but it doesn't go to 255, it only goes halfway to 255. And then C only goes halfway to 255 again. This is called variable length subnet masking. And even though it might look easy to visualize here, it can be a lot harder when you're thinking about it, but we'll go through the same process again. So let's switch back and look at it from the magic number perspective. So what we're looking at here is a situation where we're starting with 50 hosts. We're going to have a network with 50 hosts. We're going to have a network with 25 hosts and a network with 25 hosts. Just looking at that, that's 100 hosts. That is about half of a network that we're looking at, because we have a /24 network, 192.168.1.0/24. We're going to be using about half of it for these three subnets. And this is normally the way this question will be presented, where you're given a number of hosts and they say come up with networks that will work in this scenario. You could easily say, we only need 3. We're going to use a /26, because a /26 will give us 4 networks and they're all large enough. But frequently they will give some either a situation where you can't do that, where you need to use variable length, or they'll say you have to use the smallest number of hosts or leave the largest number of IP addresses in reserve. So we're going to start out with 50 hosts. And in order to do 50 hosts, it's the same process. How many host bits do we need for 50 hosts? Well, if we count up, we have 2. Let's put it down here. Or let's put it here. 50 hosts is 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, minus 2. So that equals 62. 1, 2, 3, 4, 5, 6. We have 6 host bits to get to 62 addresses. 5 wouldn't be enough, and 7 would be too many. So we're going to use 6 host bits. That leaves us with 2 network bits. So that means that we have a 1, and then zeros. So our magic number is 64. Now what happens here is 192.168.1.0/26, because we have those 2 network bits here plus our 24 network bits previously, that's 26. That's our first address. And because that's the size of this network, we know where our next network starts. 1.64. Except we don't know what size that next network is. We know that it can be smaller. And if we just go with the same process, 2 times 2 times 2 times 2, that is, let's put them all there. Minus 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. And that's enough because we only need 25. Minus 2 is 30. So that means for the next network, we shift where our magic number is. We shift where our subnet is over by 1, because we have 5 host bits and now we have 3 network bits. So we just variable length subnet mask this to be /27, and the next network, we add 32 to that. 192.168.1.96 well, again, we don't know the size, although it is the same size. We'll do another /27 and 192.168.1.128. This is the same thing that we have here, because I made this one simple. We'll do an example that's a little more complicated. So now the rest of this is exactly the same. This is where you can turn off your brain and we say these are networks, and then we have first, last, and broadcast. So in this case, like I said, shut off your brain. 64 minus 1 is 63. That means last is 62 and first is 1. This broadcast is 1 less than the 96. So that is 95. And here, this is 94. And then this one is going to be 1 more, so that's 65. Last one we have is 1 less than 128, so it's 127. And this is 126. And this is 97. So now let's just look at what numbers we have here. If you think about it, we are going from 0 to 127. And from the number line, that's about half of the network. The network is 256 or 254 IP addresses, 256 numbers. In this case, we need about 100 of them. And we went halfway on there. Yes, we have a little bit of waste because we said we need 50 hosts, but we actually created 62. We needed 25. We created 30 and so on. So that tells us that this makes sense. It passes the sniff test. It's the direction you want to be going. As you see, it's just the magic number shifts depending on your requirements for each individual thing. And you're not always starting at 0. In this case, you start at 0, then you start the next one. It's just like you're kind of resetting things. You're starting at 64. So let's move on to examples now. Okay, our first example kind of is not necessarily a real world scenario. And this actually is supposed to be 25 based on what I had written up earlier. So let's do 25. It is, again, our same process. How many host bits do we need to get 25? Well, it is 2 times 2 is 4 times 2 is 8 times 2 is 16. Not enough. Times 2 is 32. So that was 5 times. So we need 5 host bits. That leaves 3 network bits. So that is 1, 1, 1, 0, 0, 0, 0, 0. Now, one thing to keep in mind. When I had 15 before, 2 times 2 times 2 times 2 is 16. But the minus 2 makes it 14. So you need to go larger than that. We would be still minimizing waste when we went to the same 3 network bits here. But just to continue on where we were, this again is very similar to the last one, /27. And then the next network, that only needs, because our next network starts at 32. That's where our magic number is. I will highlight it. So our next network, 1.32. And we need to know how big that network is going to be. So 12 means that we need 4 bits. 2 times 2 is 4, times 2 is 8, times 2 is 16, minus 2 is 14. That's enough to get us 12 addresses. So we need to change that to a 1, make that our magic number. Unhighlight that. So that means that we are at a /28 now. And then we're increasing this by 16. 192, 168, 1.48. And we don't know what that is, what the next one is yet, but we'll calculate it in just a second. So the next one we need 8. If we do 2 times 2 is 4, times 2 is 8. That almost sounds good, but then we do minus 2 and that's 6, and that's not enough. So we need the 16 minus 2 is 14. It's going to be the same size as the previous one, even though one is 12 and one is 8. So we can say 192, 168, 1.64. So that's where our network ends. And again, we can calculate the broadcast, the first, last, and broadcast. Broadcast on this is 31. First is 1, last is 30. Again here, 48 is the next network, so 47 is our broadcast, so 46 is our last, and 33 is our first. And then the last one is 64 is our next network, and we don't know how big it is, we don't care. So this is 63, and 62 is our last, and 49 is our first. So that is variable length subnetting, and again, we're not using much of the network. The next example will come up with one that is using a bigger portion of the network that's available. So this is example 2. Once again, we're looking at different size networks. In this case, there's no other option. There's no configuration that will allow us to have 100 devices on one network when we subnet it /24 and still have room left over for 2 other networks. Just looking back at our picture, that is in a sense similar to this picture here. So we're going to start out the way we do with everything. How many host bits do we need for 100 hosts? And that is 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128, minus 2 is 126. So that is 7 host bits we need. So our first network has 1 network bit and 7 host bits. And this is going, well, I'll put an A in front of it. Now, I did change it from 192.168 to 172.16. Just because it doesn't matter when you're only looking at 1 octet. This could be anything. I could have put 10.0 for all of these to make it easier to type and easier to write. Just want you to be aware that it is exactly, all we're looking at is that 1 octet of interest, and everything we're changing is there. Now, the subnet mask here, it's 24 bits on the left, plus this 1 bit right here, which is 25, and that's it. Now, when we go to B, we know that it's going to start at 172.16.0. Our magic number is 128. So 128. Now we need to know how big it's going to be. And 50, just based on what you've seen before, 2, 4, 8, 16, 32, 64 is on the 6th, 2 to the 6th power, minus 2 is 62. So that's going to need 6 host bits. We change that to a 1, and we put a 26 there. 20, let's try again, 26. And then we can move on to our next network is C, 172.16.0.64 plus 128 is 192. And this network is smaller again by half, which is, as we saw before, it's going to take 5 host bits. So we just go here, change that to a 1, and we have a 27 this time. And our next network, which is not actually being used or defined, we just want to know where it starts so we can figure out where the previous one ends, is 0. And we have 32 plus 192 is 224. So that is as complicated as it gets, adding these numbers and figuring out how large these networks are. Again, I could fill in, first is 1, the last is 126, broadcast 127 on subnet A. We can continue the whole process that we've done before. So that is variable length subnet masking. It's not as intimidating, or should not be as intimidating as it might sound. Just, again, do the magic number math. If you want more examples of these and you think just another video of examples would be helpful, let me know and I'll see if I can put something together for you. If you've watched the whole video, great. Thank you for sticking around. I hope you found it helpful. That's all I have for you today. Thanks for watching.